A challenge of our generation is reducing our carbon footprint. That challenge is only going to increase as populations grow and the demand for energy increases. And as much as we may want to rely exclusively on renewables like wind and solar, the only real round-the-clock energy source that's carbon-free is nuclear power.
The nuclear energy has to be part of a comprehensive portfolio for sustainable energy. So it's not necessarily renewable, but it's green in the sense that it doesn't emit carbon dioxide. So we can use nuclear to help meet the energy demands of the country and the world. At the same time, we can reduce the emissions of greenhouse gases that are leading to climate change.
And all of the above energy portfolio is really what we should be striving for. It's ideal for renewables such as solar and wind to work in concert with nuclear power providing the baseload energy production. There are advanced reactors that are intended to address some of the concerns with the existing reactor fleet, issues preventing the expansion of nuclear power such as cost. These advanced reactors use different fuels and different coolants than the typical light water reactors of today, and put the materials that are used in these reactors in challenging environments. And so research in the area of materials behavior in advanced reactors is really an important topic that must be pursued.
Future, the fundamental understanding of transport under reactor extremes, is a project funded by the Department of Energy to look at how materials behave in the harsh environments of reactors. The materials in a reactor experience a multitude of harsh environments. There's a radiation field caused by the fission process itself. And you can think of that as a bowling ball hitting bowling pins. The neutrons fly through the system, smash into atoms, and throw them all over the place. So the material is degrading because of that. There's also a corrosive environment. Reactor materials are always in touch with a coolant, and those interact with the surface of the material and start to degrade it, just like rust does on your car. And the third harsh environment is the high temperature fields. We have large temperature gradients and large absolute temperatures that really change how fast things move in the material. Any of those environments individually would be a challenge for the material and for our understanding of the material. But put together, the synergy of those three environments really changes dramatically how the material evolves in the reactor system. Our project is focused on understanding the atomic scale mechanisms that drive the evolution of these materials. But we need to upscale that information to mesoscale models, which are more engineering scale and actually say something about the material in the reactor conditions themselves. Modeling alone is not sufficient. We can't simulate everything we would want to know about these materials and make a predictive model of these materials. So we couple with extensive experimental interrogation, both as validation for the models, but also for the models to serve as a starting point for future experimental interrogation to propose new experiments that help us fill the gaps of our models. By combining theory and experiment in this way, we hope to build a fundamental understanding of these materials that let us go beyond what we know about the materials to make predictions both on longer lifetimes and potentially develop new materials that have even better response in the reactor.
Understanding how materials will evolve in advanced reactors is incredibly important to the eventual deployment of these advanced reactors. And the future program will provide that science underpinning that's really necessary to have a predictive understanding of materials behavior.
Our first goal is to develop a descriptive understanding of materials. Can we understand what's happening at the atomic scale so we can build a physics-based model of their performance? But ultimately what we're after is a predictive understanding, where we don't necessarily have all the experiments to validate against, but we have confidence that our predictions actually have some physical meaning. Our goal is not to develop new materials, but it's rather to lay that foundation for the next generation of researchers to take our fundamental understanding and design new materials that extract the most out of the fuels that we use in our nuclear reactor systems, and overall provide for a much greener economy for our future generations.